In corrosion, moving interfaces can be used in a lot of different types of models. And one of them is anode consumption. So you want to see how your anode is consumed and how the shape of the anode changes over time. In modeling corrosion and deposition, you can model arbitrary shapes and different corrosion products and how they impact the corrosion process. And also modeling where one expect large deformations and moving interfaces between the electrode and electrolyte, such as in this pitting corrosion example. So basically we have two types of moving interfaces. One is deforming geometry or moving mesh, where you deform the geometry and move your mesh nodes. And this may need remeshing when large deformation distorts the mesh. And in general, it cannot handle change in topology. So that if you have an anode that sort of completely dissolves the moving mesh functionality, will have problems resolving that. But with the level set and phase field methods, which are mathematical representations of a field that represents the interface between the electrolyte and electrode, it is possible to have the anode, for example, completely disappearing, because it's just a mathematical field and it doesn't need to have your mesh deforming. So let's have a look at the deforming geometry first. The deforming boundary velocity is defined by the stoichiometry for dissolving and depositing species. So here in the electrode surface node, you select the stoichiometry coefficients for your electrode surface. And then automatically this will be a deforming electrode surface that is capable of moving in the model. If you use the level set method, you have another physics interface called the level set. And this also applies for the phase field that we'll look at later. But the level set equation, and you can see the level set equation here, and the parameters that you have to set. So this is from a tutorial model CPU with anode deformation. And the key lies in this velocity field here. So this is where how you sort of propagate the front of the surface of the anode over time. And similarly for the phase field method, it's a slightly more complicated equation coming from the Cahn-Hilliard equation that defines the chemical potential of the interface to ensure that the energy of the system diminish correctly. So there's another equation here that is solved. So I will have look at the interfaces and show a demo on how this functionality is used. So let's go to console. Okay, so here I got a model or a geometry with an anode sitting here in front of a big steel cylinder sitting in an electrolyte. So first I will add the physics. I go to add physics and find this electrochemistry, corrosion, deformed geometry, corrosion secondary interface. And now you can see that it automatically adds deformed geometry into the component. So now I can start adding the material first. So I just add a blank material here, 3 Siemens per meter. And then if you look at this deforming domain, you have just some settings for the type of smoothing that we use. We can go with hyperelastic in this case. Works well here. And then we have the physics, and then we have some multi-physics nodes. So here I just want to add electrode surface. So here we add an electrode surface, and this is my anode. So here I can add the following dissolving depositing species. IL 2700 and call it, that's 55. And then we go into the electrode reaction. And here we type in the stoichiometric coefficients. So it's 2 electrons. And then the stoichiometric coefficients we set to 1. And then I set minus 105 as the equilibrium potential. I can leave this Butter-Volmer coefficients alone. And then I need to set up the electrode surface for the cathode. So it's almost all boundaries like that. And then here I don't need to do anything with dissolving depositing species. Of course, if I wanted to model the corrosion of the iron, I can do that. But in this case, it's the aluminum that will sacrifice itself. So we can put minus 0.6 volts here and 10 to the power of minus 1 as exchange current density. And then the electrochemistry parameters are all set up for this interface. So now we can go to non-deforming boundary and see that all boundaries are selected. And then on the deforming electrode surface, that's only where we have this electrode surface boundary condition. So I can deselect this boundaries here because I don't want these to move. So they are now deforming boundaries. And that's it. That's all we need to set up when we work with the moving or deforming geometry interface. So we can add a study, time dependent, and let's simulate this for, say, maybe time of 2.3 years. And let's click compute. And here I get some plots of the potential. But I'm interested in looking at this total electrode thickness change. So here we can see that it has changed quite a lot over the time of 2.3 years, 2 years. And it's probably capable of deforming even more, but eventually the soil will struggle to deform this. And then you need to either do a remeshing, and in some cases that will only help you a while, because when it's completely consumed, you will have a change in topology, and that is not supported with this deformed geometry method. So we can try another model by using the level set method. So I would just remove the deforming geometry and this anode equation. Just cleaning up a little bit. Let's just delete the solver as well. So now we can add the physics for the level set method. Add physics. Go to the mathematics, moving interfaces, select level set. And here we can see the equation. So now we need to define some variables. So first I will just add highly conductive porous electrode for the anode. And as you can see, I cannot click it here because there's a difference operation here that removes this. So just add that back to the domain and add this highly conductive porous electrode. So now that's there, and here we can make some assumptions that it's an electrolyte material, and that whenever it's solid, you have an interface on the surface that is approximated with the level set function. And this level set moves, and then the interior of the anode will be solid, but the rest of the domain will become electrolyte. So here we can see that it's electrolyte in both domains, and we can start adding a few variables. So it's easy to define the variables here. So let's define a normal velocity, which should be minus CP I look here 1 divided by 2000 amp hour per kilogram multiplied with 2700 kilogram per cubic meter. So here you can see that we have this velocity now that is defined in meters per second. And then we also need to define this epsilon liquid, which is we don't allow it to be smaller than 10 to the power of minus 3 and not larger than 1. So this is a trick to sort of limit the variable that we use for the porosity. So now we can go to this highly conductive porous electrode and this is just tortuosity here. Set this to epsilon liquid and electric potential like this. And then we can go to the porous electrode reaction. And in here we type in the minus 105 to the power of 2 like in the previous one. And here comes the key that we use LS delta. And this delta function is a delta function that exists only on the interface of the level set function. So it's the integral of this equates to 1, and it's a delta function. So that means that this reaction here will only be active at the surface of this interface. So now we can start setting up the level set model. And here we have this reinitialization parameter, which should be maximum of Vn and epsilon. And we can leave this default parameter for the thickness. And then int norm x. So this is the interface normal. So that's the normal of the level set interface, like that. And then we set up the initial values, and now it's defined in all the domains. So we only want to define this equation in the anode domain. So the initial value should be fluid 1, fluid 0, and this one we can just disable. And then we need to put on an inlet on all boundaries, and set that to fluid 2. So now it will sort of fill with this fluid number 2 as which is the electrolyte as the anode is consumed. And we can try to run this and see. Of course, this method is quite sensitive to the size of the mesh that you have in the anode. So if you want to have a high accuracy, you need to have a fine mesh, and it's also a bit diffusive, this method. So you need to have control of the interface thickness and the mesh size. But as you can see, it's a quite quick method in this case. So here we can look at the volume fraction of the fluid and see that at 3 years it's totally consumed. And you can also see that with the potential that we have. But if we look at the initial time step here, so you can see that it starts out looking like an anode, and then as time goes by, it is consumed and eventually it disappears. So you can see that compared to the previous solution that where we used the deforming geometry, it was consumed rather quickly, and that has probably to do with the large mesh size that we have initially in this domain. So if you want to have more accurate results, we need to refine the mesh and adjust the parameters slightly.